Dear students, on the previous turn, we had started our discussion on web search by feedback learning. The idea is that the feedback that we have obtained from the users implicitly by watching at the actions of the user on the search result presented before them, like in terms of the sequence of clicking, the time spent, whether printed, bookmarked, emailed, saved, copied and pasted, etc. Why not use that implicit user feedback to learn from it and improve on the search performance? Okay, so that is the idea. So we need to boost up the weights of the documents being consistently picked up by the users and penalize those which are being mostly ignored by the users. So for that purpose, we are making use of the empirical document importance weight formula that we already know of, sigma d, which is WV1 upon 2 to the power Vj minus 1 plus WT Tj upon Tj max and so on. We've seen that formula a few times earlier, so I'm not going to go into it. This is our learning formula, which I had introduced on the previous turn, that for the relevance matrix, dkth location of the relevance matrix R, the I plus 1th iteration would be the ith iteration of RDK plus mu times the document importance weight, where mu is the learning formula. And this is normalized by 1 plus mu sigma d. So mu will let you have the learning speed or the learning rate. So if mu is 1, that means you want to put the entire weight into it. But if you want to make it a finer learning, then you can keep it somewhere between 0 and 1. With 0, no learning will take place. As simple as that. But this formula is so good that it ensures that not only learning takes place, which means I plus 1th iteration will be an improvement over ith iteration, but also this formula will ensure that for all values of I, the value of RDK remains bounded by 1. It remains between 0 and 1. So in the subsequent slides, let us try proving it. Number 1, RDK always remains bounded by 1, which means for every I, RDK I plus 1 remains less than 1, given that RDK I is less than 1. If the ith iteration is less than 1, then the I plus 1th iteration will also be less than 1. So it remains bounded by 1. And this is the learning formula that we have seen in the previous slide also. So given that RDKI plus 1, so I'm starting with this given point. Given that RDK is less than I plus 1, it means RDKI plus mu sigma D. So I'm adding mu sigma D on both sides, right? On both sides of this inequality. So RDKI plus mu sigma D is less than 1 plus mu sigma D, just adding mu sigma D on both sides. This implies that I can take this 1 plus mu sigma D over here, which means I am dividing both sides by the same quantity. Just as I added the same quantity mu sigma D on both sides, in this step, I am dividing both sides by 1 plus mu sigma D. So RDKI plus mu sigma D upon 1 plus mu sigma D will be less than 1, because once I divide both sides, 1 plus mu sigma D upon 1 plus mu sigma D will be 1. Okay. And what is this? This, in fact, from the formula, we know that this is nothing but RDKI plus 1. So it proves that RDKI plus 1 remains less than 1, provided that RDKI is less than 1. It means that the I plus 1th iteration of RDK will also be less than 1, provided that the ith iteration of RDK is less than 1. So this is my relevance matrix. Not necessarily a square matrix, because it contains documents on this side, document 1, 2, and so on, document M. And on this side, I have the keywords K1, K2, so on up till Kn. So it is not necessarily a square matrix. It is an M by N matrix. So somewhere here, the generate the value, the kth value of RDK, that is what I'm talking about. If the ith iteration of RDK is less than 1, then I plus 1th iteration also will have its value less than 1 or bounded by 1. So this is the first theorem or the first result that we can prove corresponding to this learning formula. Now, the second good part of this learning formula is that RDKI plus 1 is an improvement over RDKI, which means for every I, RDKI plus 1 is greater than RDKI given RDKI is less than 1. So learning will take place, and learning will take place, and simultaneously it will remain bounded by 1. So it start saturating 0.99, 0.999, 0.9999, and so on, but it will remain bounded by 1. And it will also be an improvement over the previous iteration. So again, I'm starting with the given value, given assumption. RDKI is less than 1. This time I'm multiplying both sides by mu sigma d. So should not make a difference, just multiplying both sides by mu sigma d. So RDK mu sigma d is less than 1 into mu sigma d, which implies RDKI plus mu sigma d is greater than RDKI plus RDKI dot mu sigma d, right? So, okay. So now I divide, in the next step, I divided by 1 plus mu sigma d. I divided by 1 plus mu sigma. So in this step, what I'm basically doing is that I'm adding RDKI on both sides. So it will be RDK over here, RDKI and RDKI on both sides. Since I'm taking this side over here, so I have changed the inequality. So RDKI plus mu sigma d will be on this side, and RDK mu sigma d plus RDKI on this side. Now, over here, I can take 1 plus mu sigma d as common. Okay, RDKI 1 plus mu sigma d. 1 plus mu sigma d will come. I'm taking as mu in denominator, and what remains here is RDKI. And this again is RDKI plus 1. We know from the formula, this particular formula. So RDKI plus 1 is greater than RDKI. So which means that RDKI plus 1 is an improvement indeed over the ith iteration of RDKI. So this is the beauty of this formula. It ensures learning, improvement, and it ensures that it is always bounded by 1. So with this learning formula, let's move on. Now we think that there was a single keyword query. Now what will happen if you have multiple keywords query? Q in the reduced disjunctive normal form. Q is expressed as a disjunction of reduced atomic descriptors, each of which is a conjunction of all the elements in their original or negated forms. So which means the sum of product form that I'm talking about. Okay, where Qji may be Kj or maybe Kj bar or the complement of Kj negated. Okay, for all I between 1 and m, and for all j between 1 and pi. We need to distribute appropriately the weight sigma d into all the constituent positive keywords of the query. So we'll simply take the positive keywords of the query first. The negated parts we will see later. So now there are multiple keywords. So how to distribute sigma d between them? Had there been a single keyword, we would have simply added mu sigma d to it. But once we are up against multiple keywords, how do I distribute it between the positive constituent keywords? The negative we will see later. So in that case, since there are, you see, a total of m or terms, and within the or term we may have multiple and terms. So what I'll do, instead of giving sigma d itself, I'll distribute sigma d into all these or terms. So there are m or terms, so I'll reduce it RDKI plus mu sigma d by m, 1 plus mu sigma d by m. So you can see that instead of giving sigma d, now I'm giving sigma d by m, where m are the number of or terms in the query in the sum of product form, right? May not necessarily be canonical sum of product form. Any sum of product form would do. But as many or terms are there, or as many sum terms are there, we'll divide sigma d between them before distributing it to RDK, right? So I see that this mu sigma d by m, the formula, the structure of the formula remains the same. So the two theorems that we have seen, that I plus 1th iteration is an improvement over ith iteration, or it remains bounded by 1, that will hold. Because just in place of sigma d, I'm giving sigma d by m, right? So sigma d by m may be replaced by another quantity like y or whatever, plus mu times y, plus 1 plus mu times y. So my theorem will remain intact. Now, for any negative not term ki in the query queue, suppose a document dj is picked up. What it means? It means that the document dj is not relevant to the keyword ki. That's why it is picked up. There was a negative term and the document was still picked up. So that means the document is not relevant, right? So we can subtract a penalty factor delta which lies between 0 and 1 from RDJ ki, corresponding to that value of relevance matrix which was negative for that document, right? So whatever document DJ picked up in response to the term ki, which was a negative term or a not term, we should subtract a penalty. So that means it is not relevant. So reduce it a little bit. Dealing with now linguistic and weighted queries, as we saw in the previous turn, we distribute the document importance factor sigma d in proportion to the weights associated with each term in the query. The weight corresponding to each term in the linguistic queries is calculated as the weights of the OWA operation, and the weight for each term is specified directly by the user in the case of weighted queries. So both weighted queries as well as OWA queries can easily be taken care of by having sigma d divided by sigma d into the weight corresponding to that keyword, right? So that weight may come from the weight specified by the user in case of weighted queries, and that may come from the OWA weights in terms of the OWA queries, right? Now exponential penalization. Suppose a positive term ki is in the query queue and a document dj is not touched by the user. So that means penalization is not just done on the negative word. Negative word and picked up, penalization. Positive word and not picked up, there should also be penalization. You got the idea. Negative word, negative keyword, and the document was picked up. Penalization should be there. Document is not relevant, right? So there should be a penalization, which we have seen earlier in terms of delta. But suppose a document with a positive keyword is there, but document is not picked up, so its weight should reduce. And this is very important in terms of the dynamic nature of the web. In response to a keyword, one document may be relevant today. So people had been consistently clicking it, spending time on it. Sigma D was better. So its relevance value was going up. But tomorrow, a more relevant document might come up in response to the query. So what should happen? The previous page that we had been increasing the weight, that should also come down. Otherwise, it will saturate somewhere 0.999. It was saturated and it stays there for a long time. And it comes next only when the other pages have exceeded 0.999. So it makes sense that we should also reduce the weight of such documents which were not touched by the user in response to a positive term ki. So for that, what we're doing, rdj ki r plus 1th will be rdj ki rth iteration minus 2 to the power alpha upon 2 to the power alpha max plus 1, where alpha is the age. Age is counted up each time the document dj is neglected by the user and is reset to 0 whenever a user selects that document. So sigma max is the maximum count at which the age alpha is made to saturate, right? So suppose the first time it is not picked up, so it will be 2 to the power 1 upon, suppose 2 to the power 10 plus 1, if alpha max is 10. Next time it is not picked up again, so it will be 2 to the power 2 upon 10, 4 by 10. Next time it is not picked up, then I should subtract 2 to the power 3, which is 8 upon 10 plus 1, right? But in between, somebody again picks it up, so alpha will be reset to 0. So again, it will start from 2 upon 11, then 4 upon 11, then 8 upon 11, and so on. So that should be subtracted. because this document is not being picked up, and if it is not being picked up consistently, I should have exponential penalization. Okay. So now in a real application of learning from users' feedback, the responses of actual users will be monitored. In a performance analysis experiment, it would be more convenient to use a probabilistic model to generate the responses automatically. We begin with a matrix P, where Pij is the probability of finding the term J in document I. This is taken to be proportional to the assumed importance of the term J in the ith document. In fact, this probability distribution captures the bias the users are expected to have while making their choices in selecting the documents from the results of a given query. So this is our probabilistic model for experimentation. The difference between the matrices R and P is the same as that between fuzziness, which describes the ambiguity of an event, and randomness, which describes the uncertainty in the occurrence of the document, respectively. So this part we have already discussed in detail, the difference between fuzziness and randomness. So R that we have been talking about, relevance matrix, is fuzziness, and P is the randomness. We also have a query generator that selects keyword randomly and then combine them with and, or, and not operators by the flip of coin, or the linguistic operators or the weighted operators randomly. Depends what kind of query you want to have. So queries randomly. Now, user satisfaction versus the number of user feedback vectors with the learning rate mu is equal to 0.1. So you see the training set that we are generating based on the random vector. So you see slowly it keeps on learning, and it saturates to 0.6 after several iterations, 6,000 iterations, it saturates. This is for learning rate 0.1. If the learning rate is 0.01, then it saturates much later, somewhere around 12,000. So slower the learning rate, finer the learning will be, and slower it will get. Okay. So this was about the web search by feedback learning. Right. So we have seen quite a few techniques so far. Like, for example, let me make you recall, we started with TF-IDF, then we saw vector space model, then we saw Boolean similarity measure, then we saw hubs and authorities, then we saw PageRank. So should not there be a way to combine all of them, to supposedly combine the goodness of all of them? That is what takes us to the next topic, rank aggregation based enhancement in web search. We have seen user feedback based enhancement till this point. This was user feedback based enhancement or website by feedback learning. So let us now take aggregation based enhancement in web search. So what is rank aggregation? Rank aggregation is the problem of collating a given set of rankings, may be used to declare the overall team positions based on the rankings given by various judges. So in our case, one could be TD, one judge could be vector space model, one judge could be Boolean similarity measure, one judge could be hubs and authorities, one judge could be PageRank. So that way, suppose we have 5 judges, right? So all these judges are giving their own verdict in terms of the ranking of documents. We should have a way and means to combine these rankings in order to give the overall consensus ranking. So this is the general definition. Rank aggregation is the problem of collating set of ranks. It finds application on the web in meta searching. What is meta searching? A meta search engine is a search engine which doesn't have a database of its own. Rather, it gathers the search results from several search engines, combines them, and presents the combined view before the user. So this search engine may contact a search engine which is operating on TF-IDF basis, another search engine operating on vector space model, another one operating on Boolean similarity measure, another one on hubs and authorities, and another one on PageRank. So combines their results and produce. That is a meta. Also, I'm fighting. We will see all those documents which have been illegitimately manipulated. Rank aggregation will fight them and will put them in the lower half of the search result. We will see how. We will see later. Then word association. Suppose I have a collection of keywords. I don't know how to combine them, whether I should combine them using and connective or connective or and or combination, what combination. So in that case, we have word association. You give me a combination of keywords. I'll search results corresponding to each of those keywords individually. Like K1, what is the search result? K2, what is the search result? K3, what is the search result? And then I do K1 and K2, K1 and K3, all the combinations like this. Then K1 and K2 and K3, K1 and K2 and K4, and so on. So all the possible combinations, I search the results, I do the rank aggregation, and then I produce the result. So I'm taking the burden off the shoulder of the user of combining those keywords with proper logical connectives. I've exhausted all the possible combinations of logical connectives. Then search engine comparison, a relative comparison I can do. I take the collated search result or the rank aggregated search result and compare it using Spearman rank order correlation coefficient with the results of a particular search engine 1, search engine 2, and so on. So which search engine is closest to the consensus ranking, I'll assume it to be the best, right? So now details of rank aggregation. Rank aggregation is the task of coming up with a list L such that normalized aggregated Spearman foot rule distance is minimized. We will see what does it mean. A polynomial time algorithm exists to compute the foot rule optimal aggregation for full lists. However, when collating the results from various search engines, the lists are the partial ones. We know 1, 2, 3, 4, 5. The other one is just 3, 4, 5, 8, 10. They are not completely overlapping. So the true optimal aggregation for partial lists is NP-hard. The NP-hard nature of partial foot rule optimal aggregation forces us to go back to some positional methods, right? So if you do the rank aggregation for full lists, polynomial time algorithm exists. But for optimal aggregation of partial lists, it is NP-hard. Because you never know 1, 2, 3, 4, 5. The other could be 8, 100, 2000, 4000, and so on. So are you going to take all the possible combinations? So that is why it gets NP-hard. So what is Spearman foot rule distance? Similar to Spearman rank order correlation coefficient, it is just that it is taking the mod values. So for L1 is equal to CDBAE and L2 is equal to BDECA. What is the foot rule distance between them? First of all, we will see A. A is at 4th position, A is at 5th position. So I take the mod of 4 minus 5. Then I come to B. B is at 3rd position here and 1st position here. So 3 minus 1 mod value. C is 1 minus 4. So 1 minus 4 mod value. D is 2 minus 2 mod value. And finally, E is 5 minus 3, right? So I sum all the mod values. This comes out to be 8. You can check for yourself, and half into n square. So there were 5. So 0.5 into floor. What do I mean by floor operation? 5 square will be 25. 25 into 0.5 is 12.5. So floor operation will reduce it to 12 only. Just the lower integer from the fraction value that I've got. So 8 by 12, which is 0.667. So I'll say that the Spearman foot rule distance between these two given lists, L1 and L2, is 0.667. Now, given a set of k such full lists, L1, L2, Lk, the normalized aggregated Spearman foot rule distance of this L to the selection, to the collection of all the lists is given as FLL is summation I is equal to 1 to k, the Spearman foot rule distance of this combined list with Li, which is L1, and then plus L2 plus L3 divided by the number of lists, right? So this is the normalized aggregated Spearman foot rule distance. So let me elaborate further. Suppose I have L1, L2, L3, L4, so on. So individual lists are there, right? And there is this combined list L, which is a combination of all of them. So Spearman foot rule distance is the normalized aggregated Spearman foot rule distance is the foot rule distance between this combined list and L1 plus combine the list of this the foot rule distance of this combined list L and L2 and so on, L and L3, L and L4. I add all of them and divide by the number of lists that were there in the combination. So that is the normalized aggregated. So this is this distance that I'm trying to minimize. When I minimize this distance, then I say this L is the best algorithm or the best combined list. So let me go back to its definition. Rank aggregation is the task of coming up with a list L such that the normalized aggregated Spearman foot rule distance F, L and the collection of lists is minimized. Okay. So by now you can understand the definition. Rank aggregation is the task of coming up with a list L, combined list such that normalized aggregated Spearman foot rule distance of this F, distance F of this combined list with the collection of lists that is minimized, is minimal, right? If such a foot rule optimal aggregation is done, then only spam fighting will be effective. Okay, which means that any rank aggregation algorithm that follows the minimization of the aggregated Spearman foot rule distance, such a rank aggregation algorithm will ensure that an illegitimately manipulated page goes in the second half of the aggregated list L. Now, positional Bodas method is the first one, the simplest one. This is a positional method. Given k lists L1, L2, so on, Lk. For each candidate Cj in the list Li, we have assigned a score SICJ, which is Cp, such that Li of Cp is greater than Li of Cj, right? The candidates are then sorted in a descending sort order of the total Boda score, where it is the summation. Let me take the example and then see. Suppose I have two lists, L1 and L2. So what is the Boda score of A? Boda score of A is the number of documents that are below this A in the list 1 plus the number of documents that are below this list in the below this document in the second list. So over here I have just one document E below it, so 1, and no document below it, so 0. So Boda score of document A is 1. Likewise, Boda score of B in the two given lists, 2, because A and E are below it, and 4. So 2 plus 4 is 6. Boda score of C is 4 plus 1, which is 5. Boda score of D is 3 plus 3, which is again 6. And Boda score of document E is 0 plus 2, which is 2. So these are the Boda score of each document in the list. Had there been one more list, L3, then how many documents are below A in the list L3? That will be added up here. How many documents are there below B in the third list will be added up here. Fourth list, likewise, I go on adding the Boda score. Okay, so let me go back. The lists L1, L2, Lk for each candidate Cj in list Li. For example, in our case, A, B, C, D, E are the candidates in the given list L1 or L2 or L3 if there is any. We assign a score Si of Cj, right? Cj in Si is Cp, where Li Cp is greater than Li Cj. So all such documents which are below it, the candidates are then sorted in decreasing order of the total Boda score. So now when I sort them, I see that B should come at the top in the aggregated list. In fact, B and D are tied up for the top spot, both having the maximum Boda score 6. Next comes C. After that, we have E, and after that, we have A. So what I can say using positional Boda's method, when I combine these two lists L1 and L2, the combined list or aggregated list will be BDCEA, or you can say DBCEA. CEA. The tie will just resolve arbitrarily. So this is the simplest method for carrying out rank aggregation, and this is the Boda's method of rank aggregation, right? So we will stop here. On the next turn, we will see more methods carry out rank. Thank you very much.